All right, so in this video, we're going to talk about an integration technique referred to as integration by parts. We'll start by coming up with a formula that we're going to use to take advantage of this method, and then we'll talk about identifying the parts, and then we'll jump into a few examples. So first things first, we're going to take the derivative of u times v. Derivative of u times v. Now this is a product, and so the derivative of the first would be du times the second plus derivative of the second back times the first. So really nothing special there, just went ahead and listed out the derivative using a product rule. And so now we're going to move some things around. I'm going to have a u dv over here on the left, and it's going to be set equal now to the derivative of uv minus v du. So again, I moved some things around. Essentially what I did is I moved this guy over here, hence it being negative, but I wanted to write it in such a way that it's going to make more sense here in a second. So from there, now we'll go ahead and we'll actually integrate both sides. So we're going to integrate all the way through this. And on the left, we're going to have this integral of u dv. And on the right, for that first term, the antiderivative and the derivative are opposites of one another, so that leaves us with uv, then minus the integral of v du. And so this is our formula for integration by parts. And as it sits here now, it probably doesn't look like it's doing much for us, but it will. And so what we're going to do is now, when we're given an integral, we're going to have to identify different parts. In particular, we're going to have to identify the u and the dv. Since this is what we're starting with, and we're going to use this formula, we have to identify both the u of the integral and then the dv as well. So I'll come over here and I'll say choosing parts. There's going to be 5 different things that I'm looking for: inverses, logs, algebra, which is pretty vague, trig, and exponentials. So in choosing our parts, we're going to start with the inverses and work our way down in selecting the u, and from the bottom working up and selecting our dv. Now again, if it's not making a lot of sense right now, that's perfectly fine, but it will, I promise. Just give us a minute till we get into an example. So when it comes to remembering these things, you might have heard, or it's pretty common to hear, ILATE, I-L-A-T-E. So in selecting your parts, just remember ILATE: inverses, logs, algebra, trig, and exponentials. So I'm going to go ahead and clear the screen now. We'll look at the first example, and I promise you as soon as we get through that first example, this screen will make much more sense. Okay, so the example we're going to look at here is going to be x times cosine 2x. And I would encourage you, for all of these types of problems, run through your standard integration techniques thus far. You know, can you manipulate it algebraically or trigonometrically? Can you use a u sub directly? Whatever it is. But in this particular case, we're going to move forward using integration by parts. Now remember, the formula is here. So this guy right here represents this integral. We have to identify both a u and a dv. So when I come over here now, I need a u and I need a dv. So from our last slide, when we talked about ILATE, we go down in order to select the u first. Do we have any inverses? No inverses. Do we have any logs? No logs. Do we have any algebra? Well, the algebra, as I mentioned, was pretty general. This x by itself would be considered algebraic. So I would let my u equal x, and then everything else has to be the dv. So the cosine of 2x dx. So everything you see here has to be the u dv. We've separated in parts by the u and the dv being x and then cosine 2x dx. Okay? So now, if we want to take advantage of this formula, we're going to need u and we're going to need v. Well, to get v, we're going to need to integrate this guy. But we're also going to need du. And to get du, we're going to need the derivative of this guy. So our du in this case is going to be a dx, and our v right here is found by integrating. And you can certainly go off to the side and do a u sub here. U would equal 2x, du would equal 2 dx, divide it off, etc., etc. And this comes down to be 1/2 sine of 2x. Okay, So once we've got that, now we can move back into this formula right here. We would have u times v, so x times 1/2 sine 2x. So x times 1/2 sine 2x minus the integral of v du. So minus the integral of v du. So we're going to have minus 1/2 integral sine of 2x dx. And now to finish this thing off, we have one more smaller integral. It's going to be integrated similar to how we did it up here by using a u sub. U would equal 2x, etc., etc. So you can certainly do that off to the side of your screen if you need to. So 1/2 x sine 2x. Then it turns out to be plus 1/4 cosine 2x plus c. Again, this comes from the integral of sine being negative cosine. So we have that negative creating our plus. And then from the u sub, we add an additional 1/2 out here, giving us our 1/4. We also don't want to forget at the very end to tack on that plus c, since this is a definite integral. An indefinite integral. And so now we have our final answer. So again, hopefully after one example, that previous screen starts to make a little more sense. We'll work several more and in the same exact way where we identify the parts and then let the formula take care of the rest. All right, so for this example, we're going to look at the integral of a natural log function. If you think back, we've done some integrals with natural logs, but they've always been set up in a way to where there's been additional parts allowing for a u sub. But if you really want to get to the foundation of the integral for a natural log, it's going to have to be done by parts every single time. Okay, so we'll go ahead and we'll start identifying our parts. We need to pick a u and a dv. So I'm running through the I-late. Inverses no, logs yes. So the natural log of x squared plus 4, and then everything else would be our dv. So in this case, dx. Now, having done two problems so far where we've selected our u and our dv, if you look at that I-late list that I gave you, the reason why it's been constructed the way it has is because it allows us to get from our u to our du by differentiating, and our dv to our v by integrating easily. So for example, if I put my natural log of x squared plus 4 over here, doesn't do me any good because my next step to bring it down would be to integrate. So the reason we've constructed this list in order to select the u is an ease of differentiating when necessary and when integrating when necessary. Okay, so that gives us our du now. So that's going to be 1 over x squared plus 4 times the derivative of the inside, which is 2x dx. And then on the dv, if we integrate, we get our x. All right, so now we have uv, so x, natural log x squared plus 4, minus the integral of v du. So that's going to be a 2 with an x squared on top, and x squared plus 4 dx. All right, so now we are ready to integrate this guy right here. Now, this is a little bit of an unusual integral. Most of the time, these work themselves out to where it's relatively straightforward and simple, at least something we've seen many times in the past. But this is one where we have to be a little bit creative on. Now, there's more than one way to do this one, but I find that the easiest way and a technique that's actually quite helpful moving forward is to add 0. All right, so if I take this thing and if I add 4 and subtract 4, this is going to allow me now to group in such a way where I can take my single denominator and go up into both of those separately. All right, so let me go ahead and write that out because I know that's a little messy. So we have this x ln x squared plus 4. Then we have minus 2 with our x squared plus 4 over our x squared plus 4 dx. And then we'll have a plus 8 integral 1 over x squared plus 4 dx. Okay? So again, all I did is I took this x squared plus 4, divided it under this guy, and then I have my negative 4 and my negative 2 giving me my positive 8. Then I have my 1 over it for this guy here. Okay? And you can see in doing that, this just ends up going to 1, which is then a very simple integral. And this one over here works perfectly into our inverse tangent. Okay, so let me go ahead and carry this just a little further. So x natural log x squared plus 4 minus 2x. And then for this last one right here, this is going to be a 1 over 2 inverse tan of x over 2, right? Our a value in this particular case. So a squared equals 4, therefore a equals 2. So using our inverse tan function, that's going to be an 8 over 2 inverse tan x over 2 plus c. And then my final step is just to clean it up a small bit. We'll say that's plus 4 inverse tan x over 2 plus c. So while it's not unusual that we end up with inverse trig functions when it comes to our integrals by parts, the adding 0 part here is just an interesting technique that I thought I'd bring to your attention before we get too far in this chapter. It'll be nice to have that as an additional tool moving forward.